in our last sample problem 5.7, we used this kind of manipulated version of PV equals nRT. So P times the molecular weight equals density times RT. We used this to actually calculate the density of a known gas. And what we're going to do now is find out the molar mass of a volatile liquid. So we're going to use that same equation, but we're going to use it in a different way. So again, I'm going to use my same type of a philosophy here in terms of writing down information that we know and where we want to go. So information that we know. Well, we know that the volume of a flask is 213 milliliters, and this is going to equal the volume of our gas. So this is a volume of flask equals a volume of a gas, because remember, by definition, the gas will expand to fill the container that it's in. So in this case, the volume of the flask equals the volume of the gas. The temperature of this gas is 100 degrees C, and we know that because we put this liquid from a petroleum sample in a flask, which we know the volume of, and we put the flask in boiling water so that we vaporize this liquid. So we know that the temperature of this vapor is going to be 100 degrees C, because that's the temperature of boiling water. So again, we vaporize this liquid, it fills the flask with the gas, and she's going to fill that flask with the gas until all of it has been vaporized. Then she's going to close the flask, and then she reweighs it. So again, we've got the volume of our flask, which equals the volume of the gas, the temperature of our gas, which again will convert this to Kelvin, so 373 Kelvin. We know the mass of the flask plus the gas and the mass of the flask. So if we take the difference of these, hopefully that's pretty obvious to everybody, we're going to get the mass of the gas, which is 0.582 grams. So that's the mass of our gas. So our mass of our gas is equal to 0.582 grams. And the last piece of information that we know, again, obtaining the following data, that the pressure of the gas is 754 torr. And we'll see in our next problem kind of ways how we can get the pressure of the gas by maybe collecting it over water or so forth. But she knew that the pressure of this gas was going to be 754 torr. So again, if we think about what the question is asking us, where do we want to go? Calculate the molar mass of the liquid. So basically, we want to know the molecular weight of that liquid that she's converted to a gas. So using, again, our derivation that we had from sample problem 5.7, we can use, again, as a known piece of information, this equation. The pressure times the molar mass is going to be equal to mass over volume, which is density, times R times T. So again, temperature is given, the pressure is given, we know the mass of the gas and the volume that it's contained in, and R is a constant, so we're ready to solve for the molar mass of the gas, which is what we're interested in. So again, I'm going to solve my equation directly for the variable I'm interested in. So the molar mass of the gas is equal to the mass of the gas times R times T over the volume of the gas times the pressure. So in this case, again, 0.582 grams, 0.08206 liter atmosphere per mole Kelvin. Temperatures, again, 373 Kelvin. Volume, and again, we need to have this in liters because that's the units of our R. So I'm going to do a mental math here, 0.213 liters. And pressure is given in torr. This is an atmosphere. So a quick calculation to convert this to torr. I'm going to multiply by 760 torr. 1 atmosphere, I should say. I'm going to end up dividing by torr there. 760 torr, so that's 0.992 atmosphere. 0.992 atmosphere. And the molar mass is 84.3 grams per mole. So pretty straightforward problem in terms of using a kind of manipulated version of PV equals nRT, now to find the molar mass of a volatile liquid. So how this problem could kind of be a more advanced problem is maybe now you have to use this information to actually identify which gas it might be. Maybe there's 5 different gas options, and you have to maybe think about the molar mass of all 5 of those gas and pick the one that has the molar mass closest to our experimentally determined one here. So lots of ways that this could be a basic skill that you use in a more advanced problem.